This conference will now be recorded.
Hello everyone.
Yes, good morning, everyone. Can you slow down the fan? Yeah, good morning, everyone. Screen and audio both are fine or not? Please confirm. Okay.
It's fine.
Okay. Yes, Devya, you have any question? Yes, everyone, is it audible? Uh, Manjusha, is it audible and visible? Yes, please confirm that audio video is okay. Audio and display is okay. In chat box, you can confirm. So for those audio video is not okay, right? You check your settings or network connectivity. This is a demo session for physical design, right, which is conducted by VLSI Guru. So you all are from recent pass out 2022, and others 20 recent pass out 2026. It's online. Can you just write in chat box if you are recent pass out or 2022 or 23, 24? So can you just please mention? Okay. So most of you, okay. Okay, so I got an idea. So most of you are from recent pass out 2026, right? Apart from that, 2017, 2024, right? 2022. Okay, fine. So how many of you are MTech pass out? PhD and MTech? You are MTech? BTech. How many of you are MTech or PhD? Okay. How many of you are working professional? Means working in weekdays? Power electronics. Okay. Anyone else from MTech? We are not able to hear. Nitesha. Nite- Okay. So I got a rough idea. So I was asking how many of you are working professional, working in weekdays, not available on weekdays, working professional? No one is there working professional? I think except one. Okay, Shilpa and Divya. Okay, fine. So,
Hi,
as you
sir.
know,
This is Shilpa, and I'm
yes.
a working professional, but right now I'm in IT. I just want to switch my domain from IT to electronics.
Oh, okay, it's fine. So you are currently working, or you have put up the papers and you have
No,
time?
I'm currently working. I'm working with Deloitte, but the only problem is I don't want to continue my IT job. It's been 10 years I'm working in IT, but right now I want to make a shift and want to explore the chip designing field.
Okay, it's okay. Okay.
Yeah.
So we have that kind of facility also. Those people who are working, for them also, the plan is scheduled with respect to the working people, those who are not available on weekdays. Okay. So I'll be explaining and taking all the queries.
Will now be recorded.
Yes, sir. So this is physical design demo session. So as you know that physical design is not just a specific course, right? It is part of complete VLSI design cycle. So when we talk about VLSI design cycle, what does this mean? So first of all, so before starting, right? So let me explain you, let me ask you one question, that what is VLSI first of all? What is VLSI? Anyone? What is VLSI? So you came here, right, by some motivation or something, by someone has suggested, maybe possibly, right, or by reading somewhere. So what do you understand by VLSI? Anyone who can answer this? So physical design is not separate thing, it is a part of VLSI design cycle. Yes.
Very large scale.
Very large scale integration of what?
Integration.
When we say very, hmm? Logic circuit, is it true? Very large scale of integration of a logical circuits, is it true or very large scale integration of transistors?
Transistors.
Transistors, right? It is a
Yes.
large scale integration of transistors, not the circuit. Of course, those transistors will be are the building blocks for circuits and logical bigger circuits and systems, subsystems, right? But yes, the basic level abstraction or the basic level component is transistor only, right? But what kind of transistor? That is also big question. What kind of transistor device? So when we say VLSI, right? You are saying it is a very large scale integration of what? Transistor, right? Transistor means what? Transistor, what transistor? So there are many types of transistor, right? Which transistor we are talking about? Can you name few transistors? BJT, you can tell that BJT is a transistor,
FET.
right?
NPN transistor, PNP transistor.
Right. So all the FETs, right? So you can say that MOSFETs, right? So you can say that there are N MOSFET and P MOSFETs, right? So there are
FinFET.
JFETs, right? So we have also FinFETs nowadays, right? So on, so on. So these all are some examples of transistors. But which kind of transistor integration we are talking about here? Whether is it BJT or FETs?
FETs.
FETs. Why FETs? Why not BJT?
So it's an older version of transistors, BJTs.
Yes, one reason correct. One reason is low power operations. We need devices with low power. And correct. Area, very good. So area is also very important here. So compared to BJT, FETs are very small, right? And it is low power consuming. And what else? These are the two main major reasons why we are picking up FETs, right? Because it is easy to fabricate on small area. So more complex design can be accommodated in small region or small area. That is called, we are saying that we are integrating all the transistor to form one circuit, right? And we know that BJT is what? Current control device or voltage control device?
Correct.
Correct? Is it? It is current control device, whereas FETs are MOSFETs and these are voltage control devices, right? And BJT gives what? Inductive behavior, whereas your FETs shows capacitive behavior between two layers. So these are some basic difference between what? BJT and FETs. You might have already read all these things. So transistor means what? Transistor integration of MOSFETs, right? Or if it is a FinFET technology, then it's called as FinFET. So MOSFET devices, right? So integrating where? So integrating to get what? Integrating to get some circuit. Now what circuit? Any devices, any circuit, right? Any circuit which can be again integrated to get one subsystem or a block. Now that block can be integrated to get a system, subsystem, and many subsystem can integrate into a system. Now what kind of system? What are the applications? What are the applications? Many applications, right? Can you give me any example of VLSI chip application which you see in daily basis? Processors. What processors? Mobile processors or laptop processors, system processors, right? And that's all. You are using electronic gadgets. RAM, ROM, okay, memories, and many, yeah. See, microcontrollers, no, not microcontrollers. You can say microcontroller also, but yes, so the basic chip can be developed. So I'm talking about application where it can be used in daily basis, right? So those are many
Automobiles.
component is what.
Automobiles.
Yes,
Sensors.
yes.
Automobiles.
Sensors, automobiles. See, sensor again, that is a component, like I said. I'm talking about application, the end product, automobiles, right? Now you're seeing ADAS system, right? What is ADAS system,
Advanced driving assistance.
right? It is kind of autopilot mode in cars, in four-wheelers, right? So that is only possible due to VLSI chip. Any other example? The AC nowadays we are having 6 sense AC with inverter inbuilt. Now we are not having separate stabilizer to control AC voltage drop or voltage fluctuation, right? Any other application?
Home appliances, IoT.
IoT, right? Home appliances. So smart homes. Nowadays we are having smart homes. You are staying at workplace and you want to switch off your fridge. You can switch off your fridge from at home, from your workplace itself. You want to start the washing machine while staying at your workplace. You can do that also. You can switch off complete power staying from somewhere from the remote area. That can be done by smartphone IoTs, right? And you are wearing what? Smart watch. So smart watch also has so variables, well, right? All variables, right? Wireless variables has semiconductor chip. And nowadays we are having specs, right? Specs or what we say, smart specs, smart goggles, right? Glasses. And
House
so there
cleaners
are
with house cleaners with some automotive chip. It will clean the house.
yes, so you have seen there will be circular vacuum cleaner, right? Just you need to set the mode. Automatically, it will clean your house floor, right? You don't have to carry it with yourself. You might have seen in some video or any advertisement. So that is also possible because of semiconductor. So there is a whole. So why I am telling this? There is a whole lot of big market, right? Which is now shifting towards automation or shifting towards what, and that automation can only possible by semiconductor chip or VLSI chip. Okay, now when we talk about integration, right, integration of devices to get all these designs, right, these are different designs or not, you need different design because it is application specific, right? That is why we call it as ASIC. What is application specific? Application specific integrated circuit, right? So when your design is, so your design circuit is integrated, which is specific to particular application, those kind of chips are called as application specific integrated chip, right? Now which is versatile chip? Now this is application specific. This can be performed only for specific application. If you have designed a mobile chip, it is good for mobile only, not for your laptop, right? But then what is the versatile chip? Versatile means what? Flexible chip which can be operated for any application, right? So it is a kind of, you can tell that it is a universal chip. Is there any such chip? Yes. So those are called as programmable chips. Now you have heard or read about guided missiles, right? So some DRDO has developed guided missiles. What is guided missile? That it can be guided any point of projectile motion, right? So once missile is launched, Now decision has been changed that after 100 after like 1,000 kilometers, now they have changed the decision that we don't want to hit at target 1, we want to hit at target 2. Can that projection or the projectile trajectory path can be changed? Yes, it can be changed. That is only possible if your chip is reprogrammable, right? See, if it is application specific, it is fixed to that application. You cannot change it, right? Suddenly, if you want to change everything, right? How it is possible? Only by reprogrammable chip, like FPGA. What is FPGA? Right? Only because of reprogrammable chip that is possible. You might have heard about one mission called as Chandrayaan, right? Recently, I mean last year or last to last year. So they sent one rover, and so they drilled into the moon's surface, and then they taken samples, which is of course for research basis, to find out whether there are any traces of water or not in South Pole, right? So how they were operating from Earth, or how they are controlling that how much like what samples should be taken, how they are monitoring, how they are controlling. If it is application specific, suppose washing machine chip, can you tell washing machine chip to switch on the AC? Can you tell washing machine chip to check my messages in smartphone? So it is very specific to that application. It will only take those controls or those orders that to wash the clothes or to dry the clothes. It is fixed there. So if the chip has to be flexible, so it has to be reprogrammable, and that is only possible by FPGA kind of chips, right? But there are different of course cost and disadvantage and advantages is there. Understood? So major part of industry covers, right, is ASIC only, 85%. So whatever you see in commercial market, right, so that is ASIC based chips only, right? Very less 10% to 15% of chips are there which is reprogrammable, because making cost is very hefty, right? And there are a lot of complexity also, right? And it is very dedicated to some special operations, or even in medical equipments these reprogrammable chips are used, right? Nowadays we are having nano operation, or we say microsurgery, right? They are not going to open you completely up, right? They are not going to cut you and then do a lot of operation. Now they are having microsurgery. They can insert small thread like, which will have some camera also, and then they will do all the process. You might have seen in some video or something. So nowadays that kind of technology is also there. So yes, so whatever we are going to discuss, it is application specific integrated circuit. Okay. Now, when we talk about integration, so we have talked about integration of circuit, right? And that circuit is developed by basic brick that is called as MOSFET device, which is a transistor, right? When we talk about a small component called as inverter, and we talk about CMOS technology, right? So how many transistors are required to get an inverter? How many transistors are required? MOSFET transistors. If you are using CMOS,
Two.
right? We require 2 transistors. Right? We require 2 transistors. This is input. This is output. Now this is what? PMOS and NMOS. So 2 transistors are required. Suppose now if I want to design something very big, right? Let's say MUX, right? MUX has how many inputs and how many outputs? Mux has how many inputs and how many outputs? Let's say it is 2:1 mux. How many inputs and how many output? Two inputs, one output. Is it correct? Sure. Yes. Online. Is it correct? How
One
many
select
inputs
line.
and
Yes, yes.
One select line.
so there are three inputs,
Three inputs. One select line.
right? There are not two inputs. There are three inputs and one output. Hmm? Right? Now, how many combinational logics are required to design a mux? 2:1 mux. So, what is the expression? What is the Boolean expression? Right? We can say this is the Boolean expression for 2:1 mux. So, how many combinational logics are required to design a mux?
Three required, sir.
How many?
Three.
What are those?
Two OR gates and one AND gate.
Two or two and?
Two AND.
Two and one
OR
OR
gate.
gate, right? Is it sufficient to design a 2:1 mux? If we
So
take
not
two
gate also required.
and one OR, right? So we will require one more combinational logic that is called as inverter, right? So this is our out I0, S0, I1, right? So there are three inputs, one output. How many combinational logics are required? Four combinational logics are required. Now the question rises, right? How many devices, MOSFET devices are required, transistors are required to design one inverter? Just now we have said, you have said, so using CMOS technology, how many transistors are required?
Two.
Can you tell me how many transistors are required for AND? How many of you have CMOS subject in your graduation? You have CMOS subject in your graduation? CMOS you never studied? It was not
Four,
there.
sir.
Nowadays they're keeping, right? CMOS. So how many transistors are required?
Six.
Six. Six or four?
Six.
Four.
Hmm? So it requires not four, it requires six. Why six? Because we need inversion behavior. CMOS gives what? So you will be learning that in basics. CMOS gives what? It gives inversion behavior, right? So this also requires six. So how many total number of transistors?
20.
20 transistors will be required. Of course, this can be optimized and you can reduce number of transistors also. But if we just go by basics, so by 20 transistor, you can develop 2x1 mux. Now, if you want to design 2x1 mux, right, 20 transistors are required. What if it is a 4x1 mux? How many transistors are required? So you can calculate very easily, right? So question is, from 2:1 mux to 4:1 mux, what is happening? from 2 cross 1 mux to 4 cross 1, what is happening? Transistor count is increasing, right? Now if you go to 8 cross 1 mux, what will happen? Again transistor count will increase. Let's say I'll give you small area. Now how transistor physically look like, right? What is the physical transistor look like? So you will have one substrate, right? And then you will have, what is this? Diffusion layer, right? We don't know what diffusion layer. Let's say it is N plus, highly doped with N-type material in substrate, which is a P-type, right? Now this will behave as, so if we give oxide layer and then on top of it gate terminal, right? Metal, right? And then source and drain. Is it correct? Source and drain? Have I marked correct, or I should mark drain and source like this? Which one is correct? Drain and source not correct? Correct or not? Both are correct. Why? Because MOSFET devices are bidirectional. It is only based on how you are biasing the voltage. So based on voltage biasing, you can mark source and drain. So both are correct. It is only because how we are connecting it, right? So if we want to get the CMOS, right? So you also need to get what?
అంటే బొమ్మ చూసారు అంటే అంటే
Yes, please.
ఎవరో
You can mute if you don't have any question.
మా బట్టి ఆమె చదువు రాదురా ఎవరికి ఏమి డిస్ట్రిబ్యూట్ చేస్తాను ఆమె చదువు రాదని మేము ఇన్నుకుంటాం మేము వాళ్ళని డిప్లొమాలో నేను వండితే బొమ్మ అంటాను నొప్పి టైపు ఎన్ టైపు ఇందులో చెప్పారంటే మళ్ళీ ఉండే అందే అని అడుగుతారు VLSI మాది VLSI అందులో వాడు బాగా ఇస్తారు కాబట్టి ఇల్లు
Sir, you can mute it from your side, sir. You can mute it from your side to them.
Okay.
You can mute there. You can go there where the person is talking.
Yes. So then we have this what? So to get a PMOS, we cannot just create a P diffusion. Why? Because it is already a P substrate. To get a PMOS, we require N substrate, and that can be developed only by if you have N well. So this is N well, and then you have P diffusion layer, right? This is oxide, then again gate, metal, right? So I'm not marking source and drain. It is only, you can mark source and drain only because of how you are biasing the voltage, right? You have to bias properly, then only you can mark it. So we have PMOS and this side NMOS. This is a physical MOSFET, right? Physical CMOS. When we say physical, what does this mean? It is no more logical. Whatever we have drawn, inverter, CMOS inverter logic, that was what? A logical CMOS, symbolic CMOS, right? It is not the physical, it is just a logical, or you can say symbolic CMOS inverter. But what about this? This is a cross section of physical CMOS. If you take a CMOS device, right, and cut it into half, you will see this, right? And what is the top view of the CMOS? So I'm just drawing the MOSFET here. So if it is NMOS, you have substrate, right? And then you have poly, right? That is what gate. This is gate, one can be source and one can be drain. This is what? Diffusion layer. And then you have substrate. This is what? NMOS. Same way, if I want to draw the top view, so how I should draw? So you will require what? N-well, right? And then there will be diffusion layer. Which diffusion layer? Which diffusion layer? In PMOS, it should be doped with P-type material, P diffusion layer. So P-type material must be diffused in what? In N-well. Then only we are calling it as P diffusion layer, right? And here we have substrate. What substrate? P-type substrate. This is also P-type substrate. That is why you see P-type substrate is common. Understood? This is what N-well. Now this is what device is, or the physical device which is going to be fabricated in where? Silicon, right? Silicon material, right? Now how this silicon material, you are getting this silicon material from where? What is the raw material of silicon? Sand, right? How many types of semiconductors are there? Silicon and
Germanium.
germanium.
Germany.
Which one is better, silicon or germanium?
Silicon.
Why silicon is better?
Abundance.
Yes, it is abundance and cheaper compared to germanium. But it is only with respect to cost. But if we talk about giving the better results, better performance, if we pick based on material, which one is better? Germanium. But it's costly compared to silicon, not abundant, right? So this silicon will make cheaper designs, right? Germanium makes costlier design. It's not like germanium is not used for designs. Of course, there are very specific rare chips are there which is only used for research purposes or very dedicated operations. This germanium will also be used. Similar to, like, there are a lot of conductors, right? What are those? Copper, aluminum, and so we have silver also, gold also. All these are conductors only, right? Even iron is also what? Conductor only. But which one is best?
Iron.
Which one?
Aluminium.
Copper.
No, in terms of conductivity, which one is best?
Copper. No,
Sure.
gold.
Right? So how you are judging it? How you are judging? Based on its resistivity, right? If resistivity is less, if resistance is, so what is the resistance, right? It is rho L by A, right? So resistance is directly proportionate to resistivity. If resistivity is low, definitely what will happen? Resistance will also less and conductivity will be higher end, right? So of course, so out of these two materials have lower resistivity compared to these three materials, right? Now, so we cannot use gold and silver. Of course, gold and silver is also used. It's not like it's never used. So if you see in earlier days, there are Pentium 4, Pentium 3 Intel processors, right? If you still open the package and you will check, so people are mining gold from Pentium 3 and Pentium 4 from Intel processor. So there were times where gold is used, right, in commercial chips also. But nowadays we are only using in missile based chips or satellite based chips or space programs or medical appliances. There gold is used as a conductor, right, to have a better performance. That is why those devices, and that is why you come to hear that these missions, space missions, are very costly. How it is becoming very costly? Because everything they will take the calculation to a very precision number, to very deep precision they will take. Okay, so out of this, copper is best. Why? Because it has other disadvantages like rusting, right? Aluminium is having different disadvantages. What is that? Now we also talk about melting point, right? Which one has highest melting point?
Copper.
Highest or lowest?
Highest.
Aluminium has lowest melting point, right? Or highest?
Lower. Lower.
Lowest, right? In lower temperature only it will start melting off. It is malleable, right? Whereas copper has more strength compared to iron. Is it correct? No, copper has more lower melting point compared to iron. But why we are using copper?
Resistivity. Conductivity.
Because compared to copper, compared to iron, it has less rusting effects, right? So oxidizing, how materials are getting oxidized, that is also important or not. Your material should not easily get oxidized. So there are a lot of things you need to take care. You cannot just say this is perfect, we'll use it. You have to take care of other different parameters. So this is material level we are talking about semiconductors and conductors. So out of this, in semiconductor industry, we use silicon majorly. It's not like these are not used, I'm telling. These are also used with different requirements, right? Now, this silicon is extracted from sand after melting it, and it is melted in a structure, cylindrical structure called as ingot, right? A cylindrical structure which is called as ingot, and then this is sliced, right? Sliced into what? So you take a potato, right? How potato chips, or we call it as wafers, potato wafers. Have you heard potato wafers? So how it is cooked? So first you take a potato, right, and slice it into what? Wafers, right? Similarly, this cylindrical ingot, silicon ingot, is sliced into what? Multiple wafers, right? So it will look like disc, a circular disc like this, right? Now in this, billions of transistors can be fabricated, right? So in this small area you can fabricate millions of transistors, millions, right? Like that you can fabricate many millions of transistors or designs or systems in this, on this semiconductor, right? Silicon is that base material which is pure silicon, which is naturally p type, right? Now where your mux will be there, mux requires very small area, a dot, very less, in micro scale it is required. And if we talk about a processor design, right? Processor design size is your fingernail, total area of that system is your fingernail size. How much your size of your fingernail is there, right? So that much area is required. How many processors can be designed? Many thousand processors can be fabricated on this silicon wafer, right? It will look like this, and usually it is fabricated in this way, and then this will be cut out into different chips, and then it is packed into a packaging that is called as packaging stage, right? Where these all are connected, those are called as interconnects, right? This is your chip, this is your chip, this is the package, outer package. Now here you will have pins. Understood? This is a rough process I'm telling. Again, in the course, we will be explaining you the detailed steps, right? How it is fabricated, what are the material physics, right? So I'm just giving briefing on the material physics and what is the fabrication process, right? And the device physics. What are the device which is used? How physical device or the layout looks like, right? And then how a logical definition is converted into a combinational logical definition, combinational logic definition, and then that is converted into transistor level definition, and then we are having the physical definition of the same logic, right? Now I will, before starting, right, so we will be discussing more on the physical aspect, right, physical design as we say, and whatever we have discussed on the first slide, so it is all logical. Whether we have talked about any physical aspect here, any size, no. But if we talk about devices, now this has specific length, right? This is called as what? Channel length, right? This is called as channel length. Now, so you might have heard technology node. Have you heard? How many of you have heard this term technology node?
Yes, sir. Yes, sir.
28
Two.
nanometer technology, 90
What?
nanometer technology, 10
2 nanometer.
nanometer technology, right? You might have heard this technology node in nanoscale. What
Yes,
does
sir.
this mean?
The area between that gate to channel, I think.
Right? It
Between.
is the length between source to drain diffusion layer, right? This is nothing but channel length. But this channel length, again, when you will be learning CMOS, you will understand that this is not the effective channel. There are a lot of shortcomings due to which your channel length will shrink, right? It is not the effective channel, but let us understand for now time being, we'll say that it is nothing but a channel length, right? If we talk about 28 nanometer or any 90 or 14 nanometer, right? Now when we say channel length, right, then device, we are talking about this device, right? Where is the channel length? This is nothing but the channel length in top view, and this is called as width of device. Clear? This is called as width of device. This is length. Clear? Now you might have uh, also, right, formulated or derived what will be the current, what will be the drain current or driving current, right? So you might have learned cutoff region. Transistor behaves differently in cutoff region, linear region, and saturation region, right? So how many modes of operation are there? Regions of operation are there? Cutoff region, linear region, and saturation region. So most of the applications are there in, when we talk about ASIC. So it is in saturation region. What is the equation for MOSFET in saturation region? Mu n Cox W by L VGS minus VTH whole square by 2, right? Now you understand what is this width and what is this length. You got the idea? What is this width and what is this length, from where it is coming? Understood? Now we can clearly understand that if length is reduced, right, it is inversely proportionate to current, right? And if width is increased, what will happen? Again, current will increase. So what we have observed, that power consumption is reduced as device technology node shrinks, right? What happens to width? If width is increased, if size is, so I have this transistor, right? I have another transistor which has more width with same length. Length is same, but this is width 1 and this is twice of width. Which one will have more current? Driving current. Which will provide more driving current? Of course, second one, because it is proportionate to width. Understood? So like that, we will also understand in physical design that how driving strength can be controlled of devices. So this is, let's say we have one inverter 1 and inverter 2, right? So both the inverters are having different drive strength, we can say, only based on controlling the width. So this is equation based also, we will understand, right? Okay. So I'll just brief you on the course before I explain more on the physical design. I'll quickly brief. Just so I'll be discussing course structure, right? And how the placement support will be given. And I'll discuss also that what will be the structure in interview preparation. And so let me check when it's. Then I'll explain a SIG design flow, like what is our design cycle, complete design cycle. I'll just brief you what are all different things. Now it will be easy to understand. So what is the difference between designing and fabrication, right? So you have seen how a mux can be designed. I've also given some briefing on fabrication also. Now we'll see more that how it differentiates. Some physical design concepts I'll discuss, and then we'll proceed. So this course will be for at least for 6 months. It can be extended for 7 or 8 months also, depending on different circumstances, right? If the batch is fast learner, definitely they will end up completing the course in 5 months or 6 months. So if batch, so there will be some batch which will be taking some time to absorb things, right? They might require more time, 7 months. So revision sessions and these things will be given. Based on that, time may extend to 7 months also. But on an average, it is seen that in 6 months, course are getting completed, right? So first stage will be the PD basics. As you already are graduates and you just recently passed out, and many those who have passed out earlier also, 2022 or 23 or 20. So for them also, they will require some sort of revision and brushing up your basic topics, right? So we will not covering all the basic subjects in your graduation, like network theory and all. That is not required here, right? So PD basics will be for 2.5 months. What is required to start understanding PD advanced topic, that will be covered here, right? Next will be PD advanced, that we will cover in 3 to 4 months or sometimes 4.5 months also. Okay. Next, so what is covered in PD basics, as you can see here. So the first important core subject which is required, that is digital system design. So that we are going to understand here, right? And next important subject is CMOS design basics, right? So these two subjects are very important to start learning physical design. Apart from that, to work in lab, right? So you need some basic, because industry works in what, which environment, Windows or Unix, right? Industry works in Linux or Unix environment. It does not works in Windows environment. So we will be also teaching you about Linux and Unix commands, so that you get familiar with that format, right? And then GVim basics will also be taught. What is GVim basics? It is just a text editor, right? So you are using Notepad, right? Or Notepad plus plus, right? So it is a text editor with commands. You can use commands to manipulate text editing, right? It is very useful in our industry. Then we will also teach one scripting language, that is tool command language called as Tickle language also, right? Which is very useful. Why it is very useful? Because whether we talk about any tool, any electronic design automation tool, it operates in Tickle, right? Their core code is written in Tickle structure only. It is very friendly to those tools. So if you learn this script, then we'll also teach some basic physical design flow, so that it becomes easy to grasp the advanced topic once it is started, right? Now these are the basic structure, basic subjects which will be covered in this basic sessions. Now, what are the class timings? So if you are opting for, uh, so class timings on weekdays will be Monday to Saturday, which will be for 3 hours, and weekends it will be Saturday, Sunday, which will also be for 3 hours, right? So Monday to Saturday will be the session. One day will be holiday. It is not mentioned here, but I am telling one day will be holiday for you. That will be on weekdays, not weekends. Okay. So each and every session of basics or advanced or lab or theory session, all the sessions will be live. There will be live session, there will be offline session, there will be online session, and all these sessions will be recorded and uploaded in your InSkill user portal, where you can access that videos any point of time, right? Any time, 24/7 accessible access will be provided to you for those videos. Sure, Shravan. We can talk in the end of session. Okay. Now, here there will be two batches. One is weekdays batch, one is weekend batch. So weekdays batch are specifically designed for those who are just graduate and those who are available to attend in offline session, right? And weekend batches are for those who are working professional, who does not have time, or who are who are working or who are studying overseas. Overseas means maybe in United States, right? So they have different time zones. So for them also it is not feasible to attend the weekdays classes. So they can also opt for weekend batches. So for weekend batches, they won't have any session in weekdays. They will have only sessions on Saturday and Sunday. So both the theory part, the theory sessions and the lab sessions, both will be covered on weekends only, for only weekend batch for working professional. Those who are graduates and can attend through offline or online mode, or their availability is there in weekdays, they can attend all the days, Monday to Saturday and Sunday also. For them, structure will be Saturday, Sunday will be theory sessions, and weekdays will be your complete lab sessions. Okay. So there will be no like theory session in your weekdays. Okay. So basically that is we follow for the PD advanced structure, not the basic structure. So basic structure is like theory and some lab. Those will be in parallel in class. There will be no lab separate sessions. It will be merged sessions. Okay. The next is the phase 2 is the PD advanced session, which will be for 4 months, right? So here that complete all the topics will be dedicated to specifically physical design only. We will not talk about the design verification or layout here. That will be covered somewhat in basics, but in PD it is completely dedicated to PD, where we will be providing you the EDA tool access also. As you know that EDA tools are licensed tool. What is EDA? Electronic Design Automation Tool. It is like you might have worked in PCBs, right? PCB design you have done or not in your college as a part of practical or project. Have you heard PCB? So how you have designed? Maybe you have used some software, Eagle software, right? Eagle software will help you to design the PCBs. Or in long back it was manually drawn by pen and paper, or the pencil and paper. But from last 10 years we are having those kind of CAD tools. So EDA tools is a kind of CAD tool only, but it is used for electronic design automation. That is why we call it as EDA tool. Now there are two major players in EDA tool. One is Synopsys and second one is Cadence. So both the tool facility is present in our institute. So we will be starting from Synopsys ICC2 tool, which is very user friendly and easy to learn, and the different stages like floor plan and PNR, which is very helpful, right? So tools like DC means design compiler, ICC tool, Fusion compiler, ICV, prime time, and star RC. Okay. So here design compiler is used for synthesis here, and ICVs are for the layout, prime time is for STA, and star RC is for RC extraction. Okay. So here course structure, the class structure timings will be from Monday to Thursday. Friday will be holiday in advanced session, right? Where lab sessions will be conducted, as I said, on weekdays. On weekends, that is Monday to Saturday and Sunday, you will have PD theory session. Okay. And time is flexible. Sometimes there will be morning session. It depends on trainer and trainer's availability and the requests. Okay. And lab sessions will be as usual on weekdays. This is for regular batch. And if for working professional, those who are not available on weekdays, they can attend only on Saturday and Sunday. So morning session will be theory session for them, and afternoon session will be lab session for them. This is only for working professional, right? Clear? Any question on timing, class timing or course structure? Any query? Okay, so these sessions will also be recorded every day after session completes, and it will be uploaded in your InSkill portal, so that even though you might miss due to some genuine reason, you can rewatch it. If you did not understood that concept one time, you can again rewatch it. So that access will be present throughout your course duration, right? After the course duration, that will expire. Okay, so once you have sincerely completed the course, attending all the session, right, then we will be providing you support that can help you in improvement, in assessing your progress, right? For that, we have regular tests and assignments which will be given to you after each stage which is getting completed. Suppose we have completed floor plan in physical design, then you will be provided with some assessment, assignments, or some test, right? So that you monitor your progress, as well as you will have that assignment question and answer material which will be ready for you and you're writing, right? So mock interviews, so in this assignment, not only theory questions, there will be some lab based questions will also be there that you have to perform in lab. Okay, and then you have to give some result based screenshot and all. Then regular mock interviews will be there. If certain point of time where you have completed your PD advanced session, will be start giving you mock interviews. Okay, so that you can assess where I am standing, how much I know, whether my communication skills are lagging, is it good or not, whether I am able to express. So I have seen many students that they know very much, they know all the basics and the advanced topic, so they are good in knowledge, but they are not able to express what they want to say. They know it, but they are not able to say it, they're not able to express it. So that is also your disadvantage, right? So knowing will always not be sufficient. You should be able to communicate also. For that reason, for communication skills, we are also providing you soft skill sessions also, right? Which will be helpful in your interview preparation, right? So regular soft skill sessions will also be there, so that whatever you are learning, you will be able to express in interview, right? So those soft skill sessions or mock interviews will be followed by feedbacks also. How you have performed, which subject you are not, which topic you are not clear, you're not able to answer. What is your problem? Whether you are able to not form the sentence in English, right? Whether you are not able to express or communicate to the second person. So all the feedbacks will be given to you so that you can work on it and improve yourself. Okay, so this is where which will be help you in different things like improving the knowledge and improving your communication also, and assess your progress, right? So this will be helpful in your placement. So this is the overview of what will be the placement process, right? So first, complete the course, both theory sessions and lab sessions sincerely and regularly. Do not miss any class, whether it is lab or theory, you should not miss any class. If you miss, because it is a 3 hour session, right? So again, to cover everything, you will only feel burdened and you will start losing the interest. So you should not miss any class, right? Second is clear all the internal test which is given to you. Do not miss, do not give excuses that I am not prepared, I was somewhere else. Try to give all the internal test which is given to you. Attend all the regular mock interviews again. So people will be giving excuses, I am not prepared, sir. So postpone it. Don't do all this. Whatever you have prepared, attend the mock interviews, right? You are able to answer or not, it's okay. We'll be giving you the feedback. Okay, you are this topic is not prepared, prepare it. So next mock interview, you should come with that preparation. In that way only you will progress. But if you skip mock interviews, so you will never be able to find out where I am lacking, where is my disadvantage, right? Third is the interview preparation sessions will begin. Suppose, okay, many students are not able to answer properly, not able to communicate and tell the answers. So dedicated interview preparation session will also be given so that you will be able to learn how to answer questions, how to answer tricky question, right? So those things will be discussed in interview preparation session, right? It will also, that interview preparation sessions will also help you in resume building. So what should be the content of resume? You cannot just write anything. So it should be proper formatting, proper the fonts should be there, right? All those will be helpful in your placement. So last is the final interview, the real interview, the real opportunity will be provided to you. And you have to appear that interview with the hiring partners. Okay. So that is the last part. Only if you clear 1 and 2, 3, these things in good sincere way. So people from management, they will be tracking you, monitoring you, observing you. So if you are good enough, they are saying that you are good in all these 3 steps. Definitely you will land up on 4 and they will provide you with good opportunities. And definitely no one can stop you. You will clear it if you clear the first 3 steps. Right? So let us take a break before I explain you about the flow and the design cycle, right? So we'll go through some design cycle and we'll understand that where physical design lies and what are the challenges in physical design and how it can become interesting. That we'll cover after break. Let us take 10, 12, 10 to 15 minutes break and then I'll take questions also. Okay. Yes, we'll resume our session. So I guess that you are clear in course structure, what we have discussed before break, right? Do you have any question on course structure, on timings? If you have any doubt, any query, you can ask me. Okay, we'll move to next slide.
So
So
lab
let
will
us,
be purely offline, right?
okay, so let me stop you.
So
So
lab sessions will be purely offline, right?
let me answer that. So
Okay,
lab
sure.
and theory. So both are available in offline as well as online. So for online, we'll be providing you VPN access, right? So that you can use lab license, right? Or tool license from anywhere, from any remote area. Theory will also be both offline as well as online. And all these sessions will be live recorded. Live recorded and uploaded in your in-skill portal. Yes. Any other question regarding timing, course structure? No question? Okay.
Sir, are you going to cover Verilogs?
No, there will be no Verilog session. Physical design engineer do not require to learn Verilog. Not required for physical design engineers.
Not even the basics.
So in basics, you will have digital system design. We will be covering the design concept, but we'll not cover the HDL language here. HDL language is part of front-end design, whereas physical design is a back-end. Is any other question?
Hello.
Yeah. Yes, please tell me.
So, sir, are you going to take the entire session or the basics or the advanced, how it is? Can you introduce yourself?
Am I going to take the session?
Yes.
So it depends on availability of trainers and whether that slot is free or not for me. Okay, if I am available at that time, definitely I'll be taking your session. So usually this is checked and this is checked by the person who is managing the schedule. So they can better answer this. You can check with the manager on this. Any other question regarding course structure and timing?
Sir,
Hmm.
sir, does attending the lab offline make any difference, like between online and offline?
See, always it is preferred that you, if you are available in Bangalore, right? So it is always preferred that you go with offline mode. So it is very helpful. What I have observed from my past batches, from my past experience, I am telling that it is my view. So you can be comfortable in online also. It's okay. You, if you feel comfortable and you are learning more far better in online mode, it's your choice. But I felt, as per my views, what I have observed from my past batches, I've seen that students who are attending offline are more active and more attentive and more fast grasping compared to the online. So it's all your preferences. I'm not saying that it's online is a not a better option. Online is also a better option. So it's all depends on your mindset and your preferences. So here, if you are in offline, you can easily interact with the trainer and you can clear your doubts or something if it is there. It's not like in online, I will not be clearing your doubts. In online also you can ask question. You can I will be answering all those questions, right? So depends
Thank you,
on
sir.
your preferences. Some people like offline, some people like. So if you are available near to or institute or Bangalore, you can attend. Any other question? Okay. So if any other question is there, I'll take in the end of session. Okay. If you have any question, you can ask then answer. So what is the difference here between a chip design and a chip fabrication? So we are learning here about what? Chip design, not about fabrication. So chip designing is always starts from the basic logic design, and then that logic design is converted into a physical implementation or physical design. So here are the basic difference between the fabrication and the design. So design is the first stage, then it goes to the fabrication, right? What it involves: designing the architecture or logic or layout in integrated circuit, as I explained, right? Remember? And if you compare with that fabrication, whatever we are designing it, like mux, we have designed it. Physically, we have designed and connected all the combinational using all the transistors. Now it is design is complete. You have checked all the parameters. Now it can be sent to fabrication. Now what fabrication plant will do? So they will have different set of systems, right? Robotic systems will be there. So they will be helping to fabricate, means whatever your design is there, it will fabricate on the silicon substrate or silicon wafer, right? So who does it, right? Design, who is designing it? So there are many fabless companies like Qualcomm, AMD, Nvidia, right? So there are many fabless companies. Now what are fab based companies? Which has which can design as well as fabricate. See, Qualcomm or the AMD, these people can design, but they don't have their own fabrication lab setup, right? But there are companies like Intel, Samsung, TS, Intel, Samsung. These companies can design the processor or any chip, and they can fabricate in their own foundry. Okay, then what about Nvidia or AMD, right? Where these people send their chip for fabrication. So now they will, most of the time they will send it to TSMC, right? TSMC covers TSMC covers. So Harshita, this is a physical design demo session. This is not the design verification session. So if you are talking about front end, so that design verification is part of front end. I will explain the flow there. You can understand if you just wait for 20 minutes. I'll be explaining you that also. Which part comes in front end and which part comes in back end. So who does it, right? So TSMC, Global Foundry, CIMIC, these all are what? Fabrication labs. Now, what are the tools used in designing? So we have already discussed there are synopsis based tools, there are cadence based tools, Innovus, ICC2, Fusion Compiler, right? Prime Time. All these tools are used to design a chip. And what are the tools which will be helpful with respect to the fabrication? Caliber, Tcent, PVS, these are the tools which will be helpful. What are the process? What is the design cycle? I mean, not design cycle, what is the cycle of process? So in design, the process starts from RTL coding. First is the architecture, specification, architecture, then RTL, and then your synthesis. And then comes your physical design, right? And at last, verification. Okay. So process in fabrication has photolithography, etching, doping, and deposition. So all these processes are part of fabrication, right? Have you done this anywhere in your graduation, right? You haven't done? You have done. You have not worked on PCB layout. So what you have done in PCB? First you will take what? A copper clad, right? And you will take one design, maybe printed from Eagle software or something else, right? So that will have the connectivity, copper connect, the black marking will be there, right? For the interconnects. That you will imprint on what? Copper clad or not, right? Why you are imprinting on copper clad? What is that black color, that interconnect marking you are doing? What is that? How it is behaving? It is behaving like a photo resist, right? It is resisting photons. That is why you are imprinting it. Then what happens? What is the next process? That is called as etching, right? Etching means something you are taking off that clad, right? You are etching off that copper material. Where? Everywhere? No, not everywhere. Wherever photoresist is not there. What is that? Wherever that your black interconnect you have drawn, right? Wherever it is not present, that will be washed off. That copper will be washed off. Where copper interconnect will remain, wherever photoresist is present, right? That is called as etching process. Etching means removing something off, right? So etching process is done under some chemical uh, process, right? What is that chemical material which will be used? So you will take one tub or something, right? And you will add water, and then you will add some chemical component, and then you will dip that copper clad into that tub, and then you will continuously moving it under sunlight, right? Why sunlight? So sunlight has UV rays, right? So that is acting like a photons. So what is the chemical process? Under that chemical component, I think perchloride solution is there, and under that, if photons, UV photons are passing on top of that copper clad, what will happen? Copper reacts and it will wash off from that plastic material. And wherever photoresist is there, that black color, so black color material which is drawn, right, that will block UV photon, uh, UV photons it will block, right? That is how that copper material under that photoresist is saved. So when you wipe off that black color material, right, which the circuit you have drawn, you will find that copper interconnects are properly drawn. That is how complete process is done to get a PCB, right? Then you will mount component and then you will do soldering, right? That is the different part, right? But the first you should get the interconnects, right? So that is called as the terminologies are same here also. Photoresist, photolithography, etching process, right? These processes are same as fabrication, but doping is not there. Doping is not there in PCB. Why? Because what is doping? Adding impurities to get new material, right? So basically it is a simple silicon material, a p substrate p type, right? If you want to make it behave differently, so you have to add impurities, maybe pentavalent atoms, maybe trivalent atoms. It will behave differently. That is called as doping, diffusing impurity. That is why after diffusing the impurity, it is called as diffusion layer, right? If you diffuse it with pentavalent atoms, it is called as N-type, right? It is called as N-type material. If you diffuse it with trivalent atoms, which is whole majority, right, which will give what? P-type material. So like that doping process will be done, right? Like I have shown you here also, right? So initially this single substrate layer is there. So first there will be etching process, etching of the substrate, and then forming the enwell layer. How enwell layer will be formed? by doping. Doping by what? N plus impurities. Pentavalent atoms will be doped and injected to get what? N well. But before that, you have to etch it off, right? So after this, again you will dope with P diffusion to get P plus or P type material. Here also you will etch off and then you will dope it with trivalent atoms, P diffusion. Like that process goes from bottom layer to layer by layer by layer. It goes from bottom to top. So in the end, you will see top view like this once process is completed, fabrication process. Then comes interconnects. So these terminals will be connected to interconnects based on the connection, and that is done by metal layer. Okay. So what will be the final output? So GDS2 will be the final output in design cycle. GDS2 is nothing but a graphic design file, right? Whatever we have designed, MOSFET design, all physical structure, right? The interconnects, the metal layer connects, all are physical structure. It has width, it has length, some dimension, right? Everything is defined. Which layer is used? Diffusion layer, substrate layer, N-well layer, metal layer, poly layer, all will be present there. GDS2 is a non-readable file. You cannot read it. It is a binary file. Okay. But the information will be present with respect to these layers only. All layer information will be present. It is an encrypted format in binary format. So what will be the output of chip? So this GDS2 file of design, which is the final output, which will go to the fabrication lab, right? And they will use this file as an input to get that fabricated on silicon wafer, right? Now, what are the dependencies? So design people or designers rely on foundry rules, right? Or manufacturing based rules. So they cannot just design anything they want. They cannot take width they want, right? They cannot change length of MOSFET. They have to follow whether manufacturing capability is there or not. Means what? Whether foundry is allowing or not. Okay. Suppose you want to order a bakery, right? And you want to order, make 100 cupcakes, right? You want to order in bakery. So that bakery can say, okay, we can cook 100, bake 100 cupcakes in 1 hour or 2 hours. They will give deadline, and they will tell you, okay, this should be the design and this should be the size. You will tell my cupcake color should be pink color. On top of that, there should be cream and there should be. You will tell some your specification. What is your demand? What is your requirement? They will tell, okay, we can do that. Suppose now you want cupcake in quantity of, let's say, 1 lakh. I want 1 lakh cupcake in 1 day. Right? What that bakery will tell? No, no, my shop is small. I don't have that kind of machinery to bake 1 lakh cupcake in 1 day. First, he rejected there itself. That bakery does not have capability. Second, now your expectation is that every cupcake, so you might be, you want those cupcake for some kids birthday party, right? You want some cartoon characters, some Mickey Mouse, Iron Man, something you want on that cupcake, that kind of design, custom design on cupcake. Now what that bakery will tell? No, no, we cannot do that. We don't have that capability to do custom designing on cupcake. So again, they will not agree because they don't have capability. So before designing, a designer must know what are the rules, right? Whether foundry is allowing us to do that or not. Then only you should start designing. So that is where the dependency comes on designers from foundry. Okay. And fabrication people also have dependency on design team, right? So what is that? They should get proper GDS2 file, which should not violate any rules given by them. Suppose already bakery has said, do not design cupcake size more than this, but you have designed it and send it, and they are feeding that input into their machinery, and that cupcake is not getting developed with that size. So what they will tell you, are you have not followed my rules which I have given. So that is why they are also depending on design team that they are following the foundry rules or not. Okay. What is GDS2? Like I said, it is having the information about all the layers. So I have drawn also, right? This is the top view of CMOS inverter. You can see these are diffusion layer. The blue color one is the metal layer, right? And red color one is the poly, right? It is connected. Both PMOS and NMOS is connected. So which one is PMOS and which one is NMOS? Right? It is connected. So GDS2 file will have all the circuit, all the devices. This is just one inverter. Like that, there will be millions of inverters. There will be thousands of mux. There will be thousands of full adder. All will be interconnected. So all this kind of information is present in GDS2. Right? It is kind of layout. It is not actual layout, but yes, you can tell that it is a layout information which is present in GDS2 file. Now ASIC also I have explained, right? What is ASIC? Can you answer? It is an application specific integration of circuit, right? That is by integrating the transistors, right? We know that millions of transistors, billions of transistors are there, and millions of interconnects are there, which is connecting that. Now we are just not integrating it. We are integrating to get better performance, better power, and low power. I mean, better means low power and area constraint also. Suppose you want to design a processor for mobile phone and you are designing very big, right? Then mobile size will also increase, right? You cannot carry mobile size of purse size. Means ladies purse, not gents purse. Okay, so if your mobile size is of size of ladies purse, so it's very difficult to make calls and carry it. It will be very heavy, right? So area is also very important. It should be least. So if you are wearing a smart watches, right, it is a wearables, so the chip size should not be very huge or big, so that you cannot carry it. If it is a half kg of your watch, right, then what will happen? You will not purchase if it is a half kg smartwatch. So area is a very big constraint, right? Not only this, so if area is increasing, then yield will yield will also be less. What is yield? Yield is the, so you so many people might be here from farming background also. You might be knowing what is yield. Yield means, so you have farm plot and you are growing rice, right? So there are small plot. If it is a small scale farming, right, every small plot will give same amount of rice. Is it every plot will give same amount of production of rice or
No.
different? Definitely different, because maybe some plot will get more water, maybe some plot soil quality or some different circumstances are different, right? So all small farming plots will not give same amount of rice production, right? So that is called as yield. Yield of one plot is different from other plot. Means you have same area, same input, but yield is different. Means production is different. Okay. So similarly here also. So we have wafer size which is fixed, right? Now out of this, how many chips you can get from that wafer, right? If you increase the area, what will happen? So you have this wafer. Now if you increase the area, let's say you have increased, and here you have small area of chips. Which one has more yield? One or two? Of course, second one has more yield, because it is by area we can observe that it is having smaller area compared to this one, right? This will have less number of chips. So what is that? So it will also affect cost. Understood? The cost will also increase. You should also take care about that also. Okay. So technology as it advances, right? Number of transistor count will also increase. How it will increase? Because technology node will shrink. Means channel length is getting shrink. 90 nanometer, 45 nanometer, 98 nanometer. When we talk about these technology node, what is the scale? How small is this? 90 nanometer, 45 nanometer. So here, whatever project we will be following, we'll be following on 28 nanometer and 14 nanometer. We have the files, right? So what is this scale? 28 nanometer. What do you understand from this? Can you imagine how small is this? Is it visible from naked eye? Can you see it? How small? So what is the size of coronavirus? Right? You know what is the size of coronavirus? Can you check and tell me in your phones? What is the size of coronavirus?
60 to 140 nanometer.
How much?
60 to
140?
140. 140.
Right. So there are different variants, so different sizes. 60 to 140 nanometer. Right? On what scale you will be performing lab here? It is on 28 nanometer. Right? You can just imagine. It is smaller in size. How much smaller? Almost 3 to 5 times smaller compared to coronavirus, right? Even under the highest means good microscope also it will not be visible. You have to use very powerful microscope to see this nanotechnology chip, right? So it is a nanotech. So you can understand how things can be complex in the real world, physical world. Okay. So as technology node is shrinking, right? If technology node is shrinking, what does this mean? You can have more and more number of transistor in design. Instead of one or two, you can integrate what more billions of transistors. That is the advantage here. Okay. So different integration levels are there. We call it as SSI, LSI, MSI, small scale integration, medium scale integration, large scale integration, very large scale integration. We have ultra very large scale integration also, ultra scale integration. So So this is the ASIC design flow, right? The first step in design cycle is specification, and then architecture design, then RTL. So we'll go one by one what is there. So what is specification, right? When we talk about specification, so you go to market to purchase something, purchase a bike or a mobile phone, right? So what you see first? Specification only, right? You will go to market and you want to purchase a bike. What you will see in that bike? What specification? Mileage is one of the very important specification. And
Pickup.
see, mileage and CC both things cannot come, right?
Pickup.
If you want a sport bike, yes, pickup. So you will get a good CC bike, right? It will have more pickup also, but you won't get mileage. So you have to think, you cannot get both. You have to think whether I'm going to purchase a sport bike, right? I want to drive it on highway, or is it for traffic use, right? Or general regular use, then you can see for mileage. So based on requirement also, or the medium scale where both are like average. So like that you will have some expectation. That is why in market we have all different scale of specification, starting from a very good mileage. If you go with Platina, right? Platina has a very good mileage, but that CC is less, that stability is less, strength is less. So things will be compromised. Weight is less. Of course, if weight is less, mileage will be increased. So that specific, that kind of format is also available. Now next comes, you want to both, means there will be some splendor or some average bikes where you will get good CC plus good mileage, like that. Then you will say that no, mileage I don't care, I want a very fast pickup, fast speed, good braking system, good suspension. All this comes under what? Specification. So you'll go in the higher sport bikes, right? It is also available, and based on that the cost will also be defined. More the number of specification, more your design becomes complex. Which design is more complex, Nano or Jaguar? So
Jaguar.
car, right? Of course Jaguar car is more complex compared to the Nano. Now you compare with Tesla. Again it is more complex because it has a battery system, right? ADAS system, right? Many different systems are there. So different, with more number of specification is there, definitely design complexity will increase. It's not like Nano is bad, right? It's only consumers requirement is there. We want in less price, good mileage, and purchasability should be there, right? So that is meeting, that is the specification, it is meeting, it is good product. If specification is not meeting, then it is not a good product. Specification requirement is there in market, that is why that Nano is there. It's not like people does not require. If not require, then who will produce? No one will produce. Okay. So in any system you have different. Now we talk about electronics, man, right? In a mobile or in a laptop processor and any chip, washing machine or anything. So you have different components. You have ALU, you have memories. Now how you are able to see graphics, right? You have graphics also. You have interfaces like USB ports or the audio socket, right? Bluetooth module is present. Audio and video modules are also present. PLL are present for clock. So like that, all different blocks are present in your design, which will be useful. Each block is connected with specification, right? Suppose if you want a laptop with high frequency, right? High frequency means faster laptop. Definitely you have to focus on PLL design. And suppose you want 1 TB hard disk, so you have to increase the memory design, right? The design becomes complex now comparing with 500 GB. Now you want, instead of 6 GB RAM, you want 12 GB RAM. Definitely size will increase, complexity will increase, more transistors you need to add it. Okay, so like that cost will also increase, right? Because area is also increasing. So this stage serves as foundation for the entire design process, which helps to meet the expectation with respect to power, area and speed, right? So we talked about the cost, speed and area, but what about power, right? It should not be more power consuming, right? It should last long for 1 day, 2 day. That is why we are having 6000 mAh battery. We are now having power saving mode, ultra power saving mode, right? Now you know why we have ideal mode also, right? Ideal mode. What is ideal mode? What is ideal mode? In mobile phone, you are using mobile phone, right? You don't know ideal mode.
Constant
Ideal
mode.
mode, just you touch or click power button, right? Press power button. What will happen? It will not switch off. It will just display is gone. It is ideal mode. It is called as ideal mode. So if you use ideal mode, that is what it is, saving power. Your display will not be always 24/7 on, right? You can just save power by using ideal mode. So these kind of things are available. That is coming from chip only. So that will help in saving power. Now low power designs have, so all the components in your design will not operate in same voltage. It will operate in different voltages, right? So suppose you are using a, you are playing PUBG or some high-end game on your mobile phone. What will happen? What you have observed on your phone when you are playing high-end game? Have you played game or not? Huh? Not played. Don't, do not say I didn't play. Do not play. Played, right? So when you're playing games, what happens to your phone? So first thing you observe that it's getting heated up, right? Then second observation, power is dissipating very faster. Second, third, RAM, right? RAM is getting more utilized. So you will see that from if you have 6 GB, easily it will go 5 GB, 5.5 it is utilized. Then fourth observation, you will not make that much of observation. Just heat it up, I'll put on side and charge. Right? Many observation you can make there, right? When you are playing high end game. That is all coming from component only, right? Why it is getting heated up? Because when you are playing a high end game, what is happening? Most of the memory is getting utilized. All memory elements are active. RAM, the active memory is very much operating. Now the processors, the CPU which is present here, it is using more clock cycles, more frequency. It does not require less, it will not work in less frequency. It requires more clock cycle, more frequency to have better smooth performance while playing game. That is why you play that game in old phones. What will happen? It will lag. Why? Because that CPU capability is not there to run that. Then your graphics should be very nice. It should be very good, right? There should not be lagging graphics. That is why now we have different types of graphics also, right? Then you will also require connectivity things, right? You should have proper internet, you should have proper display, you should have proper audio, you should have proper video. So all 90% of component in the hardware will be actively operating, right? So if something gets actively operating, so there will be power dissipation in a faster rate. That is why power will be dropping in a very faster rate, and due to which as a byproduct heat is generated, right? So heat, power, and your, what we say, performance will also degrade. You keep on playing in that heat, right? What will happen? Slowly you will observe that your gaming is getting lagged, getting hanged, not getting, not you are able to play smoothly, right? So that all things you will observe. So what is the point here? The point here is the power, right? How power is managed. So power is not a fixed component, it is a relative component. So when you are playing a high-end game, definitely power requirement, performance requirement, everything will spike. Everything requirement spikes. And when you are using WhatsApp or text editor in mobile phone or any laptop, whether we require that much amount of power, we require power when you're using text editor, we don't require, right? Simply so we don't require when you're using text editor, we don't require that much amount of power. Your power dissipation will also be very slow. It will not get heat up, right? So power is very variable and relative how it is utilized based on that. So it's very important component. So after specification, right? Second is the architecture design. Architecture design means once specification is decided, Now you have to think what all system, subsystem or blocks are required. So if you're using for mobile phones, you require graphics, you require memories, you require CPU. Like that you have to define. If you are designing a sports bike, you might require some suspension, or exhaust should be there, should be two exhausts, right? A good hydraulic suspension should be there. Braking system will also improve, different system. Tire and wheel structure, which alloy is used in sports bike, that will also change, everything will change. So all those systems are there, right? Wheel, tire and all those will be merged to get a bike design. Okay, so architecture is also very important. It is kind of block diagram, different blocks which will be used in your design, right? Next comes, after blocks are defined, what blocks will be used in that design. Okay, what is the requirement? Then each block you have to design or not. In bike there is a wheel system, anti that braking system is there, ABS is there, right? Then you have a chassis, complete body, right? These are all complete blocks. Consider them as a block. Each block will be designed separately or not. Engine will be designed separately by engine team. Wheel will be designed by the wheel team, right? Similarly, in any chip, so there are different components: audio, video, CPU. So people will be designing separately, right? And then that will be integrated. To design any electronic devices, what is the, how you are going to design it? Whether we are going to use pen and paper? No, right? So we can use hardware description language, where hardware can be described, right? It is a software design or hardware design? It is a hardware design, not a software design. So which language can be used? You cannot use C language or Python language to design the logical circuit or electronic design. For this, you need which language? Hardware description language. What are those? Like Verilog, VHDL. All these are hardware description language which helps to describe. Suppose you have 2:1 mux, right? How many inputs, how many output? Three inputs, one output, right? So what is the truth table for this, right? So I0, I1, S0. So we'll just give it. Okay, so there are different modeling style in Verilog, right? So what are those? Behavioral modeling, gate level modeling, and structural modeling. Okay, so based on which modeling style we'll pick, we can write the code for this. So in Verilog code, you will have three modeling style, out of which behavioral modeling style is majorly used. Behavioral means just you need to define the behavior, right? Behavior of this mux. What is the behavior of this mux? What is the behavior of this mass? So you don't need to define logical gate. Advantage is what? You don't need to understand what are all combinational logics are present, whether two and one or is there. You don't need to understand and know that thing, right? In behavioral, you just need to know the behavior functionality of 2x1. Whereas in structural and gate level, you need to know what are all logics are there. Okay, so here you can write if S naught equals 0, right? Then Y should be I0, right? Means output should be I0. Else Y should be I1. That's all. Have I written any logical gate here? See, Verilog code starts with module. Okay, I'm not discussing syntax here. Module name, and then inputs, outputs, wire, register. So I'm not discussing that Verilog part here. I'm just discussing the concept part. So this is the behavior of this 2x1 mux, the logic. Okay, whether I have defined any gates here. So we have discussed, right? There are four combinational logics required in 2x1 mux, two and one or one inverter. Do you see any logical gates? No, right? No need to define logical gates in behavioral model. So you have to define behavior of it. So that is what called as RTL logic design. It is called as RTL logic. So on right side, it is an example for 4x1 mux, right? So where functional behavior is defined, but this is a gate level definition, right? No, sorry, this is a data flow modeling style. In data flow, data is how data is flowing, that is defined here. You can see that here they have defined that out what is the input here, right? And what is the output here, it is defined here. So it is a data flow modeling style, right? Then comes RTL verification, or it is also called as design verification, right? Once your design, logical design is ready, so that behavior is ready, you need to verify this or not. Logical verification must be done or not. That is called as functional verification and design verification, right? Functional coverage and design verification. How you are going to define it, how you are going to verify it, based on possible inputs and what is their respective outputs. Okay, so this can be known from where? Truth table. Truth table always tells truth, right? So you prepare how many possible inputs will be there? How many number of inputs? 3 inputs. It is always 3 inputs means what? 2 to the power n. 3 inputs. So how many possible inputs? 8 possible inputs, right? So 8 possible inputs. You can how to write truth table? 0 0. So you have to write 8 possible inputs. 0 0 1 0 1 0. Like that, you have to write 8 possible inputs. For all 8 possible inputs, right? What will be the output? You have to write. So like that, you will get what? The truth table, right? Now with this code, now you are going to verify by writing test cases, or it is also called as test bench, right? Now in this you will be giving random inputs to I0, I1, I0. So you will give some all the possible inputs, and you will see whether my design, which is called as design under test, and you're giving inputs I0, I1, S0, right? So whatever test bench you're writing, test case you're writing, right? Inputs, whether my design, is it giving the desired output? Desired means what? According to truth table. Yes or no? If yes, then we can say that our design is, oh, sorry, our design is passed, right? There is no issue. If it is not giving desired output, right, then what we can say that our design is not correct. Our behavioral logic is not correct. The code which is written, RTL code, that is not correct. So it is a functional failure. Understood? It is a functional failure, or you can say that functional coverage. Sometimes what will happen? Sometimes the end of functionality will be met, but functional coverage will not be met. So that is all design verification part. So these all are logical verification. These are not physical verification. Then comes synthesis. See, till now, have we talked about gates? No, right? We are only talking about logical or behavioral structure. But to fabricate, what we require? Transistors physical model. That is MOSFET, right? And each gate is designed by MOSFET only, like inverter gate, NOT gate. It is designed by 2 transistors. If it is CMOS type, PMOS and NMOS. So for that you require what? For that we require whatever code is written, that has to be converted in gate level format, right? So whatever you have written, mux 2:1, that has to convert it into gate level net list. Net list means list of nets, right? So that process is called as synthesis, which converts from RTL logic to gate level netlist. Is it clear? Now, so synthesis process, what it does, so whatever behavioral code is written, right, it will convert into combinational logic or gate level netlist. Okay. Now this will be dumped into one file. It will be converted into one file. Now that file is called as gate level netlist file, right? Then we have DFT logic also. If you want to improve testability feature in design, right? Like what? Suppose you there are big designs, right? And you cannot test each and every net in that circuit. You cannot find out when there is billions of transistors, how you will check? It's very difficult. So for that we will include DFT. DFT, there are different what we say, there are ATPG, automatic test pattern generator. There are BIST, built-in self-test. There are MBIST, memory BIST, called as built-in self-test. Means whenever we see any faults in design, any net, or that is not giving functionally correct output, right? And we are getting wrong output in the end of system, right? How we will find out that somewhere it is wrong? Suppose you have found out that it is giving wrong output, right? How you will find out where is the who is the which net is the actual culprit, right? How you will find out? If it is a small design, it is very easy to find out. Suppose you have 2x1 mux. Suppose you are giving 0, 1, 0. So here you will get what? 0. What will be your output? 0, right? You're getting my point, what I'm saying? So instead of 0, let's say if you are getting 1 here, then what is the problem? Then this net is fault. So we can say that it is stuck at fault at 1. Understood? So this is a faulty net. So this is a small design, you can easily find out. But think about where there is a millions of billions of transistors or millions of devices. How you will identify that specific net which is a faulty? It's very difficult task if you do manually. For that only we require DFT block, scan chain block, which will help us to identify or test the device design. Here. So after that, once you get the gate level netlist, first stage is floor plan. So from here onwards, physical design starts, right? Then from here onwards, we talk about real size of devices. Here no more we are talking about logical thing. It is done, completed, designed, converted into gate level netlist. Now you have to think about area of chip. What will be my area of chip, height of chip, width of chip, right? So there are two boundaries. One is called as die boundary, another one is called as core boundary. So die boundary is the exterior boundary and core boundary is the interior boundary, right? And the logical cells which is present, the physical cells which is present in your gate level netlist, now you can start placing them. So not all the cells. So there are different cells like macros and standard cells. So first we will be placing macros. Macros are bigger elements, memory elements, and later on in placement stage we will be placing standard cells. Okay. So these are the basic steps which is going to be followed in floor plan. You have to place ports also, right? Ports like input ports, output ports, clock ports. So each uh, camera or audio video, GPU, those needs to communicate. Those will communicate through what? Ports, right? Then you have to place macros, memories, right? Then there will be some physical cells which are called as tab cells, end cap cells. Those will be placed, right? So blockages means placement blockages, where we should not place anything. Suppose at your home, right? You are starting building a house, so you'll build a compound wall, then interior design, right? And you will also define some place that this place should not be used for placement of anything. You will block it completely, right or wrong? So like that, you also provide blockages, right? Then power planning for your home also you will do electrification, right? Like you have placed a TV unit at hall, right? Where you are going to put the socket near to the TV, right? You are not going to put the socket of TV in the kitchen area, right? What will happen? Power dissipation will be more. Okay. So this is floor plan. So you have to decide all these aspect in floor plan. Then comes placement, where you have to place standard cells by honoring performance, power, and area. And that should sit respectively on sites, right? So this is divided into two types of placement. One is global placement, called as placement, and another one is called as detailed placement. Global placement is when you go into a house, new house, and you shifted from your old house. What you will do? You'll start arranging each spoon, bigger spoon, smaller spoon, like that. Or what you'll do? You'll throw all your luggage at new home or not? I'll start opening and start dressing each clothes and keeping arranging everything. You'll throw all your luggage wherever, which randomly, right? Fridge, TV. Then you will start unpacking everything and you'll see, okay, this is the good place to place TV. This is a good place to place fridge, right? So first thing what you did, that is called as global placement, or it is also called as course placement. Then you will do detail placement. Okay, this is a TV. We should place it in hall, not in kitchen. Like that, you will decide on a detailing. You are doing the detailing of placement. So that comes under detail placement. So legalizing means what? Where that placement should be actually present. You have to make sure that it should be legal placement. Now you have decided I will be placing TV, right, on some wall, right, in front of sofa, but you are placing TV in 90-degree. Is it a legal placement? It is not a legal placement. Or you are in front of fridge only, you have placed TV. It is not a legal placement. It is illegal placement. You have placed in right location, but illegally placed. Right? So you have to take care of legalization also while placing the standard cells. Then, so you have done the power plan. Power is provided. Now, very important that you have sequential cells also. All those should get clocked, right? Otherwise, it won't operate. So clock nets also needs to be communicated to all those cells. How it will be communicated? Whether we are going to directly give clock to every sequential, so there should be some strategy also, so that path should not be very long. It should not take more time to uh, clock to reach to these cells, right? It should be shortest path. For that, we will have different algorithms, right? For like H tree, hmm, H tree, X tree, pi tree. So that is clock tree synthesis, breaking down the clock tree to provide clock to all the sequential cells such that delay must be less, right? So delay, that is, we call that minimizing the insertion delay. Also to meet timing as well as power here. Okay. So routing, right? So last is the routing stage. So you have done power planning in floor plan itself, right? Then you have done clock routing. Then what is remaining? What is signals, right? Data signals also needs to be connected with each other, not. So you have to ensure that all the sequential cells, combinational cells, memories, and standard cells, their data signals are connected properly. Connected means what? See, it should not be just connect. If you connect there can be chance that different neck or different interconnect may get short with the different this thing, right? Because it is a billions of transistors. So that is the reason we will have different metal layers, right? So here also we will first do global routing. Then we will observe that, okay, there are many shorts, there are many opens that needs to be fixed. So then we'll do multiple iterations. With that iteration, we'll keep correcting, okay, this path is already occupied. So if you draw, right, if you want to connect this cell and this cell, right, this is how it is. In what possible ways you can connect? So if I draw so there are different algorithms like Steiner algorithm, right? Maze algorithm, mesh algorithm. So let me divide like this. So in what ways I can connect? So if I just number this 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 2, 3, 4, 1, 3, 4, 5, 4, 5, 6, 5, 6, 7, 6, 7, 8, 7, 8. Now, in what ways I can connect this, right? So you have to find out longest path or shortest path. Shortest path. So shortest path can be, you can just go like this and you can connect. This is the shortest path. What can be a longest path? You go like this and then you go like this, and then you connect. This is a longest path, right? But what if there is no short path? Means maybe this is already occupied by something else like this. Now, in what way I can connect? Right. So only possible what I can see. This is already occupied. We cannot use it. If you use this path, it will get short. The only possible way is that you go like this, go like this. Now this is also short only. Let's say, so this is also blocked, let's say. So this is also blocked. Right now, in what way we can go? 1, 2, 3. Okay. So if something is blocked, so if we don't have option, so then automatically your path becomes longer here, right? So that is all taken care in multiple iterations of signal routing to connect these two cells, cell A, cell B, right? All those algorithms also we will discuss while we will discussing detail routing. Okay. So in the end, once your routing stage is completed, in the end, you have to do sign off, right? Sign off is the final check before giving GDS2 file to fabrication lab. So those checks are done for timing, for power and physical verification, right? So timing, you should meet timing constraint, right? Delay constraints. You should meet IR drop, right? If your IR drop is very high, voltage drop is very high, what will happen? Power dissipation, right? Also power drop will be there. So your IR drop, voltage drop should be minimum, right? Then physical verification. So shorts should not be there. If you have shorts in your design, what will happen? Functional failure, right? Your functional verification will fail. So also DRC should not fail. What is DRC? DRC are the rules which is given from foundry. Like I said, bakery, remember? So you have to obey those rules also, which is coming from foundry. So there should not be minimum spacing violation or minimum width violation. So those should be obeyed. So in the end, after verifying power, timing and physical verification, it is sent to Fab Lab foundry. That file is called as GDS25. Okay. So these are the tools which we had discussed, and their what is the usage? It is written over here, right? Like I already said. So this is the physical design flow, starting from few checks: floor planning, power planning, placement, CTS, routing, and sign off. So this will be our flow in physical design, right? Okay, so this is the end of physical design flow demo. So I'll be waiting for questions, right? I am open for questions. If you have any doubts, any question regarding placement or course structure, timing, placement, job prospect, you can ask any question from now. I will be answering all the questions.
Hello, sir.
Yes, your
No,
name?
here in my name is Ravan, sir. Ravan.
Yes, yes, please tell me.
No, no. Here you said sign off. Sign off means everything is done with respect to physical design. Huh?
Yes, sir. So if IR means what? It is with respect to power we are talking about.
Ah,
So it will be with respect to your physical design.
okay, okay.
So in complete design cycle, starting from your RTL or specification to the physical design, if we
Mm,
talk about the time taken effort, right, or the time taken or the effort taken, so
mm,
60 to 65% is contributed or the given in what physical design. So rest
okay,
of the time 40% is consumed from front end. So
okay.
starting from synthesis, it is all called as back end. Before synthesis, it is called as front end, right? So
Mm,
if you see here, this is the complete design cycle flow. Starting from where? Synthesis. It is all back end. And specification, architecture, RTL design and RTL verification is front end design. Okay. Any other question? Any other question related to course structure, timing, or the job prospect? So I've told there are different types of company. One is fabless company, one is fab based company, right? So most of the hiring will be there with respect to the fabless company only. So there the count is more compared to the fab company. Okay, because they do not require designer. Fab companies like TSMC do not require designers. That is all robotic machines. They are doing that job. Then operator or engineer is required to operate all those machines. That's all. Not many people. Of course, Intel is both fab and fabless, means it has its own fab and it also works on design. That is why they require more number of people. And then we have service based companies also. Service based companies provide services to these product companies, right? Because sometimes they don't have resources, enough resources, so they will outsource the resources from the service companies. So service companies like nowadays, Infosys is there, HCL is there, Wipro is there, right? All these comes under service companies. Some are Mirafra or something, Insemi. These all are what? Service-based companies. So they are not designing product. They are providing resources and services to the product company. So compared to the count of companies, service companies are higher number, more numbers of service companies are there in VLSI compared to product company, which is very less. Yes. Any questions? So I'll wait for 10 minutes more. If you have any question, you can post chat box or you can directly ask.
Sir, in projects, other than this physical design flow, do we do this STA, PV, IREM, all those things also?
See, for IREM, right? Yes. So what will be the project? So at least one project will be taken parallel with the trainer, and second project will be mostly will be given you as an assignment. You have to complete, right? In that project, starting from synthesis, you will be provided with hands-on, right? So design compiler will be used. Then comes physical design. So in physical design, starting from floor planning, right, and placement, CTS, routing, all will be done in EDA2, right? So which is lab oriented. Lab and theory both will be present. So after that comes sign-off stage. So in sign-off we have three sign-offs, right? One is power, one STA, and physical verification. Okay, so we don't have a Red Hawk tool. So Red Hawk tools are used for power analysis or IR analysis. So usually it's very licenses are very costly. So we don't have that tool. But we will be doing STA sign off. So we have prime time tool. So this session will also be taken care. So this will also be given to you. Prime time session and synthesis session will also be given to you. Physical verification is done on caliber, right? But it's not like caliber is required. So internal in EDA tool, ICC tool level also you can do physical verification, but not caliber level. So it is a tool level that can be done. Clear, Lokesh?
Yes. You have mentioned ICV, right? ICV tool. What is that used for?
ICV is for layout. It is not for physical design. It is just mentioned that we have that access here in our institute. The ICVs are what? Used for custom layout. It is a layout validator
And these
from
projects are
Synopsys.
also, yeah, projects are not a low power based project, right? It is not.
It is a low power project.
Okay.
So the project which is carried over here, it is a low power project. Multiple domains will be there.
Okay.
Is any other question? Just let me call to manager. Maybe he has something to say. So the project will be carried on 28 nanometer. We also have 14 nanometer project also. So initially we'll carry with 28 nanometer, and then 14 nanometer project will also be given to you. Just give me 2 minutes. I will call. Yeah, no questions? Okay. So if you don't have question, you can start dropping off. So if you have question, you can wait. Right? Yes, today's session will be recorded. Just wait for 5 minutes. So institute manager will come here. Hmm. See about so let me tell about system specification. You have to keep a laptop with you, right? Initially in basics also, in PD basics also it will be required because you will be working on GVim, Linux and Tickle scripting, right? So the minimum specification which is required is i3 is fine. I think everyone has nowadays at least i3, so it is fine. Even dual core is also okay if you have dual core, but you have to do something, then only it is okay. Otherwise i3 is fine with the 2 GB RAM, and if you have 256 GB hard disk, that's more than sufficient. So we have a manager from our institute. He wants to talk with you, convey some messages.
Session is there.
Session is there.
Session is there.
Right.
All technical details and how many are
It
there?
is done. Technical details.
Okay. They have some doubts related to the course.
Some doubts they have asked. I have cleared them.
You have cleared. Okay. Then nothing much that I have to address.
Okay.
This. Okay. Fine.
Okay.
Can I?
Yeah, sure.
How will I be?